Hello, and thank you for attending my talk. My name is Keith Cobry, and I'm with Xi Engineering Consultants in Edinburgh, Scotland. We're COMSOL certified consultants who help clients out in a wide variety of fields, including acoustics, electronics, renewable energy, and more. In this talk, I'll discuss concepts related to work we've done on axial flux wind turbine generators for the renewable energies market. Wind power has steadily been playing an ever-increasing role in contributing to efforts to realize significant reductions in fossil fuel consumption, and a wide variety of designs are available that fill specific niches, from small-scale local onshore production to massive offshore platforms. For the design and deployment of any model, though, a few basic considerations play critical roles, including materials costs, especially the ubiquitous rare earth magnets in permanent magnet generators, long-term structural safety, where design against fatigue failure is important, and energy efficiency, how much power is produced per turn of the blade. Of particular interest to the renewables industry is offshore development, where strong continuous winds provide an ideal power source. The often harsh maritime environment, however, can make maintenance expensive. So it's critical to design such systems for maximum power per turbine, long lifetime, and an optimized generator power per mass ratio. A few principal design concepts have garnered significant interest recently with the aim of achieving these goals. One is the use of direct drive turbines, where the turbine shaft is directly connected to the generator rotor. This demonstrates a simplified construction and generally has less weight than a gearbox design. This simplicity leads to reduced maintenance requirements. With direct drive, however, one often cannot achieve the stepped-up rotor speed that would be possible when using a gearbox. The blade speed would simply be prohibitive. One way to attempt to make up for this shortcoming is with an axial flux generator design. In this configuration, magnets may be mounted to rotors on both sides of a stator plate, enhancing the time-varying magnetic flux, which is what generates the current in the coils. The coil shape may also be optimized to enhance magnetic flux, allowing denser, more parallel flux fields cutting the coil. Arcing field shapes are seen in many radial generator designs. Additionally, many radial generator designs have wire overhang, which is necessary for the construction of the coils, but is lost space because little magnetic flux cuts these areas. One of the major advantages of an axial flux design is its simplicity in construction and the resulting lower weight. The work we'll demonstrate in this talk is based on the COMSOL rotating machinery module. This is pre-configured to allow design and analysis on a wide variety of electromagnetic generators and motors, as shown in the radial flux demo models on this slide. This allows easy construction of fixed and rotating mesh assemblies. It also allows coupling to external circuits and the calculation of electromagnetically induced mechanical forces. There are two primary physics formulations employed in this module: magnetic fields with currents, and simply magnetic fields. The magnetic fields with currents module relies upon vector magnetic potential to solve Maxwell's equations, and this includes regions where currents are, for example, excited in coils or eddy currents that are induced in conductive materials. In non-conductive materials, the current term in Ampere's law is zero, so scalar magnetic potential may be used. This applies, for example, in air gaps and tends to be numerically less intensive and more stable. In our demonstration model, a rotor-stator assembly is constructed with azimuthal periodic symmetry in order to reduce solve time. Additionally, only half of the stator is constructed, with the stator midplane defined as a perfect magnetic conductor, which means that magnetic field lines pass normal to this stator midplane. This is akin to a symmetry condition. As shown, an arbitrary coil design is possible, and the rotor is associated with a rotating moving mesh, which is a time-dependent feature, while the stator is fixed. These form an assembly. The magnet array is pulled in a standard Halbach configuration in order to direct parallel field lines through the coils. In the rotating machinery module, a volume domain coil with many turns may be represented with a homogeneous multi-turn coil feature. This allows the user to provide descriptive input, such as wire cross-section, allowing the feature to calculate the coil resistance and inductance without having to explicitly resolve and mesh all winding turns. The closed loop must, however, have inputs and outputs defined. Here, since the loop is closed, an internal input plane is shown. As a result of this, the first step in a study needs to be a coil geometry analysis in order to know the nominal direction of current flow, especially if a coil has a more complex geometry. This pre-solution step is shown with the red arrows. An important facet of the rotating machinery module is the ability to connect coils to external circuits. The voltage and current values that are automatically calculated as part of the coil feature are those across and through the load respectively. In this case, a simple resistor is shown in the equivalent circuit. Circuit component nodes may be added to the model builder tree and follow SPICE netlisting formatting to describe connectivity. This allows even complex circuit components and topologies to be used. In the figure, the resulting time domain coil voltage and current are calculated as part of the coil feature. Since only a resistive load was used, as shown in the equivalent circuit, there is no reactance and thus no phase shift in the graph. It is only across the coil terminals. The power, determined by multiplying the voltage and the current, is the apparent power. In order to find the real power, which is a primary metric of interest to the generator designer, find the phase angle by solving the equivalent circuit at the rotor angular frequency. This gives the reactive inductor impedance component. The complex power triangle can then be used to determine the real power delivered to the load as work. An additional useful feature of the rotating machinery module is the ability to calculate mechanical forces derived from the electromagnetic phenomena. These forces fundamentally derive from the Lorentz forces, where an electron moving in a magnetic field will experience a force perpendicular to its velocity and the magnetic field. Similarly, a time-varying magnetic field exerts forces on electrons, putting them in motion. This is how the entire concept behind a permanent magnet generator works. COMSOL solves for the Maxwell stress tensor, which is distributed in space where these electromagnetic processes occur, and can be used to determine the forces acted on bodies. In the animation, the axial component of the Maxwell stress tensor acting on the rotor magnets and on the stator coils is shown. The left side shows the magnets, and the right side allows us to see these forces acting on the face of the stator coil. Force calculations can be defined for entire selected domains, and all data can be exported for post-processing if desired. This is often of interest, for example, in determining the electromagnetically generated torque, which is another important parameter in generator design. So that's all the time I have for now. Thank you everyone for listening, and if you are curious about this or any of our other modeling work at Xi, please feel free to reach out. Thanks again.